In our example now, we're going to do is we have a traveling wave on a string. The vertical position is given by 0.75 centimeters times sine of 6.28 times x minus 314 times t plus pi over 4. So here's our equation given in numbers, and we're going to try and figure out a whole bunch of stuff from it. This is kind of a long example, and I have a feeling that this is going to cut into Thursday's class a bit. But I am going to go through the whole example, and if this gets too long, then we'll shorten Thursday's class so you don't spend too much time at physics this week. Okay, so there's our equation. The first question asks, is this wave moving to the left or is it moving to the right? So if we want to answer moving left or right, let's think about what is the general form of our equation for a wave on a string. We know that for any general wave on a string, d of x and t is equal to 0 is equal to the amplitude times the sine of kx plus or minus omega t plus phi naught. There's our general equation. Plus means the wave is moving to the left. Minus means the wave is moving to the right. And we sorted that out with the treatment we did on the previous slide where we figured out where that general equation came from. So now let's think about A. Is the wave moving left or right? There's a minus sign here, so that tells us that the wave is moving to the right. So our answer for part A is that the wave moves to the right because our equation has the form kx minus omega t plus phi naught. And if you were writing out this answer on a test, you might throw in a few extra words there. I'll try and keep it short so this video doesn't take forever. Okay, there's part A. What is the amplitude of this wave? Okay, again, that's going to be a comparison. The amplitude is the thing that's multiplied by the sine function. It's the biggest that the wave could be. The biggest that the wave can be will happen when our sine function is equal to 1. So that means that our amplitude is equal to 0.75 centimeters. There's our amplitude. So B, by comparison, A is equal to 0.750 centimeters. You can write this in meters if you wish. 0.75 times 10 to the 2 meter times 10 to the minus 2 meters. That's absolutely fine. I'll stick with centimeters just because the number's a little easier to write. Part C, what are the wave number, angular frequency, and phase constant? Okay, that's another set of comparisons. So wave number is k, that's what comes in front of x. That's 6.28. Angular frequency omega, that's what comes in front of t. And phase constant is the thing down at the end by itself with no variable. Okay, so by comparison, we can see what those values are. So part C, our wave number k is equal to 6.28. There are no units up here, and this is somewhat typical for these kind of problems because visually it just gets a little bit cluttered. We're going to assume that x and t are given in meters and seconds, so our units on k here is going to be radians per meter. So 6.28 radians per meter. That's the wave number. Next is omega. Omega is 314. This minus sign here is not attached to omega. Omega is a positive quantity. The plus or minus just tells us if it's moving left or right. So omega is 314. The units on omega are radians per second. And that's angular frequency or angular velocity, whichever you prefer to say. And last, the phase constant is pi over 4 radians. And that just tells us that the graph, d of x and t, it doesn't start at 0. So it has a different starting point. That's our phase constant. Okay, there's A, B, and C done. Next we'll move on to D, find the wavelength and the period. And we'll find those things from K and omega. Let's just grab a fresh sheet of paper. So let's see how much I can keep on the same screen. So part D, what is the wavelength of this wave? So part D, well, we know K is equal to 2 pi over lambda, where lambda is your wavelength, the distance it takes to go from one crest to another crest. That means lambda is equal to 2 pi over K. K is 6.28 radians per meter, so we put in 6.28 here, and we get 1.00 for the wavelength. So the wavelength of this wave is 1 meter. Next is, what is the period of this wave? Well, our omega, we know omega is the angular frequency. We can write it as 2 pi f, or 2 pi over t. I'll go for 2 pi over t, because we're trying to find t. That means t is 2 pi over omega. Our omega is 314 radians per second, so we'll put in 314 here. And when we do 2 pi over 314, we get 0.0200 seconds. So our period is 0.02 seconds. Part E, what is the speed of this wave? Well, now we know omega and K, so it's going to be pretty easy to find the wave speed V. So V, remember there are two ways to find it. You can do F times lambda. You could absolutely do it this way if you want. You know your lambda. F is 1 over t, so that would be 50 hertz. Or we can say that V is also omega over K. We have omega 0.02 seconds. Oops. Omega was 314 radians per second. Divided by K, 6.28 radians per meter. Put that through the calculator. What you should get for your wave speed is 50 meters per second. And what that wave speed means is when we have this wave on the string and it's traveling to the right, this bump is traveling 50 meters every second along that string. So that's what the wave speed means. That's what that tells us. Okay, I would say A through E were the really easy parts of that question. Now let's get to the harder parts of the question when we really have to get into the nitty-gritty of sine functions and periodic motion and all that stuff. So part F says, at position x equals 0, at what times is the wave at a maximum? So when is it at the top? If we hit pause at t equals 0, if we just look at this place right here, so we're looking at x equals 0, at what time on our stopwatch is it right at the very top? When is it at the crest? So that's what we're asking for in part F. So for part F, at x equals 0, when is it at the top? Other words, so if x equals 0, d is equal to the amplitude, and we want to know what time does that happen for, what is t. So let's start with our equation. So the equation we had was d is equal to 0.750 centimeters times sine of 6.28 times x minus 314 times t plus pi over 4. Let's put in the numbers that we know. We know that d is equal to the amplitude, that's 0.75 centimeters. Times sine of 6.28 times 0, that's going to give us 0. We're left with minus 314t plus pi over 4. Okay, now we see that we have something to work on here. We know everything in this equation except t. So let's go through solving for t. So the first thing we'll do is we'll divide both sides by 0.750 centimeters. That leaves us with 1 equals sine of minus 314t plus pi over 4. Okay, one hiccup here that we often get to in these problems is that as we do calculations, let's remember our units a little bit. This is 314 radians per second. This is pi over 4 radians. So whenever you're doing anything in this unit, your calculator has to be in radians mode. So that's pretty important to remember. Okay, let's get to solving it. If we want to find t, we've got to get t by itself. The first thing we have to do is to get rid of the sine function. To get rid of the sine function, what we have to do is the inverse sine of both sides. So the inverse sine of 1, the inverse sine of a sine just leaves us with the argument. Okay, now we want to start solving for t. So minus 314t plus pi over 4 equals the inverse sine of 1. You may or may not need to haul out your calculator for that one. The inverse sine of 1 is pi over 2. So now we can solve for t. So t is going to be pi over 2, take away pi over 4, and divide it by minus 314. When we work on that through the calculator, what we get for our answer is minus 0.00250 seconds. The first thing you have to do is stop and ask, is my answer sensible? Does that make sense? This is a negative time, and we're assuming that our project starts at t equals 0. So I would say that a negative time is before our oscillation has started. So no, that answer is not sensible. So what do we do? There are two ways to go at this. I'll describe kind of in general one way, and then I'll actually do the other way. The other way you can do it is you can remember that the inverse sine of 1, it's not just pi over 2. If you did sine of 2 pi plus pi over 2, right? So if you went all the way back around, so 2 pi plus pi over 2, if you took the sine of that, you'd also get 1. So 2 pi plus pi over 2, what is that, 7 pi over 2, that would also be the right answer. So you could put 7 pi over 2 here and solve for t, and that would give you the right answer. The other way you could do it is you know that the cycle repeats every period. So cycle repeats every period t. So were we allowed to go to negative time, it would be at a crest, at an amplitude, at minus 0.0025. So it would be back to an amplitude one period later. And our period was 0.02 seconds. So the next time that's bigger than this one will be the first time it's at an amplitude. So that would be this time t plus a period, capital T. So we add this to the period, and what we get is 0.0175 seconds. So this is the first time that the wave at position x equals 0 is at the amplitude or maximum. Well, our question doesn't ask for the first time, it asks for all the times. So when is it back to an amplitude again? Well, it's back to an amplitude again another period later. So the second time, t2, is t plus 2 periods. And if you put your numbers in, you get 0.0375 seconds. The next time, we add on another period. And so on. So if we wanted to summarize that so it's a little nicer to write out, we would say that all of our times is equal to minus 0.00250 seconds plus some number of periods where that number n is 1, 2, 3, and so on. So over time it goes back and forth to the amplitudes at all of these times. So that's our answer to part F. Next we'll go on to part G, and this is going to get us thinking more about the repetition of that wave. At time t equals 0, so we're looking at a snapshot, where are the maxima and the minima? Where is the wave at the amplitude and at the negative amplitude? It's the next part we'll look at. Grab a fresh sheet of paper. So part G. So for part G, our time is equal to 0. And we want to know what is x for d equals plus a. That's the maximum. And x for d equals minus a. That's the minimum. We want to know what are those values of x. Let's start with the maxima and see, does that let us find all the values of x? And does that also let us find the values of the minimums? So for the maxima values, our amplitude is, our position D is equal to the amplitude A, so it's at a maximum. And in our equation, that's A times sine of 6.28x minus omega 314 times our time of 0 plus pi over 4. So this whole term is gone. A divided by A, or 0.75 equals 0.75. Divide both sides by the amplitude. 0.75 gives us 1 equals sine 6.28x plus pi over 4. If we want to find our x value, we have to take the inverse sine of both sides. The inverse sine of a sine leaves us with the argument 6.28x plus pi over 4 equals the inverse sine of 1, which equals pi over 2. Again, if you're hauling out your calculator for this, make sure your calculator is in radians mode because we're dealing with radians here. So 6.28 times x plus pi over 4 equals pi over 2 means x is equal to pi over 2 minus pi over 4 divided by 6.28. And when we do that through the calculator, we get 0.125 meters. We might ask, is this the first position? And if we remember that the wavelength is 1 meter, this is a small fraction of that wavelength. So yeah, this is the first place where it's at a maximum. So here's our first place. Our question does ask for all the places. Again, we could go into sine being periodic. Every time we could do the inverse sine of 1, it's pi over 2 plus 2 pi, pi over 2 plus 4 pi, and we can go through it that way. It absolutely works. But let's just draw the graph and see if drawing the graph helps us get a picture of where these maxima occur and how we could write down what that's equal to. So I'm going to draw my graph. And I'm drawing my graph, the height of the graph, as a function of x for t equals 0. I'm putting t equals 0 on the side over here, so for one time. So I know that I'm at an amplitude when x is equal to 0.125, and I know my phase constant is pi over 4. So when x is about here, I'm at an amplitude, so my wave looks like this. You know, if you wanted this to look really nice, you could plot it on Excel or something, but this kind of a sketch is okay for our purposes. So right here, this is x for our first maximum, and this x value is 1.25 meters, or 0.125 meters. The next time it's at a maximum is one wavelength later, because our graph repeats every wavelength lambda. So our maxima occur at 0.125 plus 1, our wavelength is 1 meter. And 0.125 plus 2, 0.125 plus 3, and so on. So to get the maximums, or the maxima, they're equal to x equals 0.125 meters plus multiples of the wavelength. So we can say n times lambda again. This time our n would start at 0 and go up by 1s. Okay, so there's all of our maxima. Hopefully that makes sense. So our first one's at 0.125. The next one is at 1.125 because that's a meter. The next one would be at 2.125 and so on. It goes up by a wavelength every time. What about our minima? So there's a couple of ways we could find it. And often with these problems, there are more than one way to solve it. Another way we could do it is we could put in minus a right here for our value of d, go through the process and solve for a position of x. But we've already done all that work. Let's ask, can we use this idea to figure out where these are? So for our minima, we know that we have a minimum for this value of x right here. So this is a minimum. The distance between a maximum and a minimum, that's a half of a wavelength. And a half of a wavelength in this case is 0.500 meters. So if this one is at 0.125, then this minimum is a half of a wavelength over. And then if we wanted to find all of our other minima, well, every set of minima are going to be separated by a wavelength. So wherever this guy is, the next trough is 1 meter over, 1 wavelength over. So for our minimum values, those values of x start at the first position of the first minimum, 0.625 meters. And then we add on integer multiples of the wavelength. So that's how we can find those minimum values. And again, you can do it all mathematically if you want. You can put in your minus a here. You can use the fact that your sign varies. You can put in your different values of sign and solve for it. But sometimes it's more straightforward to look at the graph and see where that takes you. Okay, we have one part left to our example. And the last part feels like kind of a simple question, but it's still worthwhile. What is the position and the velocity of the wave at x equals 0 and t equals 0? First part's really simple. We want the position, so we'll put x and t equals 0 here, and we'll find the position. And then we'll talk about how we're going to find the velocity. And it's actually a little bit of a preview what's to come in the next lecture. So it's just kind of be a little heads up to get us warmed up for the next class. So if you're a little bit shaky on the velocity, just kind of put pause on it for right now, and we'll go through it in more detail in the next class. Okay, so part H, I was using a black pen. Part H is asking, what is d of 0 and 0? And what is v of 0 and 0? So d of 0 and 0 means we fill in x and t equals 0. So it's 0.750 centimeters times sine of 6.28 times x minus 314 times t, both of those guys are 0, plus pi over 4 So you can put this in your calculator. If you do, make sure you're in radians mode, and we get 0.530 centimeters. If we want to ask, does that make sense? Let's go back to our graph, and I would say, yeah, that looks like it makes sense. So it's part way up, it's not all the way, but it is part of the way up, and it is positive. Okay, v of 0 and 0, I'm going to label this guy a Jedi problem for today. So if you're not really sure about it, and if your math skills are not real strong, you might want to skip this for right now and do it after the next class. But I kind of like putting it in here just to give you an idea of what's to come. So how do we get velocity of that piece at 0? So remember, we're looking at the string. We're looking at the string going up and down, and we're asking what's the velocity of this bit at t equals 0. And remember, this is like that problem we looked at in the first part of this lecture. We asked what is a piece of this string doing at a certain time. Well, we're asking that again now, but we're going to ask at the x equals 0 bit. How do we get velocity? Well, velocity is the derivative of position. So here's the Jedi part, is taking a derivative of that equation. So d of x and t is a times sine kx. I'm going to go symbols here just because it's a little easier to do symbols than numbers all the time. Our derivative, we're going to get into more details about this in the next class. Again, this is kind of a Jedi bit for right now. It's if you're already fairly into your math class. So to do the derivative of this guy, we can take our a outside. The derivative of sine is cosine. We get the same argument, kx minus omega t plus phi naught. And then in our chain rule, we also have to do the derivative of what's inside. And here's where we're going to talk about it a lot next class. When we do the derivative with respect to t, we take everything else as constant. Okay, so kx is constant, omega t is a variable, the derivative of minus omega t is minus omega, the derivative of phi naught is 0. So that gives us minus a times omega times cosine kx minus omega t plus phi naught. Like I said, this is a bit of a Jedi hint of what we're going to go through with lots of detail next time, so if this is a little bit blowing your mind, just kind of hit stop. You don't have to look at this part for now, and then you'll come back after we do the next lecture. On the other hand, if you're super into your math classes and maybe you like math a bit more than you like physics, then this probably makes a whole lot of sense to you. You would probably like this a fair bit. So v of 0 and 0 then is going to be minus a, 0.75 centimeters, times omega, that was 314 radians per second, times cosine of k was 6.28, times 0, minus omega, 314 times t, that's 0, plus phi naught, that's our phase constant, pi over 4. That term's gone. That term's gone. When we put that through the calculator, we get minus 167 centimeters from this centimeters right here, per second. So what that's telling us, and if you wanted to, you could set this up and you could check it out for yourself, is that this dot at x equals 0, so right here at this position, at t equals 0, if we hit play, this guy would move downwards. That's what that's telling us. Okay, that's the end of this example. It did run a little bit long, so we'll cut Thursday's lecture a little bit short.